Assalamualaikum and good day everyone. Let's continue our lecture with a new topic, signal flow graph. Okay, SFG may be viewed as a simplified form of block diagram, and SFG consists of arrows that represent the systems and nodes that represent the signals. So you can see here in figure A, B, and C. So where in figure A, you have the system GS. Okay, the system GS is represented by the arrow here. And then we have in figure B, we have a node here. So this is the node. And then this node represents the signals. And then lastly, in the figure C, you can see here is the interconnection of system and signals. In this case, we have 6 systems here that are represented by the arrows. We have G1, G2, G3, G4, G5, and G6. And then we have 6 signals represented by the nodes. And the label is R1, R2, R3, C1, C2, and C3. Okay, now let's convert the common block diagram to SFG. So in this example here, we have 3 systems. We have G1, G2, and G3. Okay, and then we can represent the system here with the arrows. But before that, we have signals. In this case, we have 4 signals, R, X2, X1, C. Okay, so we can put it into SFG. We can draw the nodes here. We have 4 nodes. We have 1, we have 2, 3, and 4 nodes here. And then we can label each node with, we have here RS. Okay, and we have here, let's say this is X2, not V2, just say it's X2S. And then let's say it's X1S, and then we have CS over here. And then we can put the systems that connected between each nodes. For example, here is RS and X2 is connected to each other using a G1 system. Okay, so that's why we have G1 here. Okay, and let's see the arrow here. The arrow here is because it is towards the X2, so the arrow is to the right. Okay, and then we have a subsystem. We have a system G2, and then finally we have system G3 over here. Okay, next one. We have another example here. We have the parallel subsystems here. We have how many nodes we have? We have R2, we have R, we have X1, X2, X3, and we have CS. Okay, so we draw 4 nodes here. We have RS, we have X1, X2, X3, and we have CS over here. And then we can connect the nodes using the arrows that represent the systems. So node RS is connected to X1 via system G1. So you have G1 here, arrow and system G1. And then node 2 is connected to RS via system G2. So we have arrow, we have G2. And finally we have RS and X3 connection via G3 system. Okay, and then we have a summing junction here. Let's see here. So there is an arrow from the signals from the system G1. We have arrow that goes into the summing junction. We have another one arrow, and we have another one arrow here. Okay, so we can represent the arrow here with 1. Okay, we have X1 that connected to CS. X1 is connected to CS. We have arrow 1. And X2 connected to CS. We have an arrow with 1. and finally we have an arrow that connect X3 to CS, and then the system is 1. Okay, next one, we have a feedback form of block diagram here, and then we can draw the nodes that represent the signals. We have RS, okay, we have RS in input, we have the error ES, we have the output CS, and then yeah, that's it. That's it. That's only the signals that we have in this block diagram. So we can connect the nodes of the using the system. Okay, so we have connection between RS to ES. So RS to ES, there is no system there, so we can represent the system with 1. Okay, and then ES is connected to CS with system GS over here. Okay, and finally we have a feedback which is from CS to ES. We have the system HS. So let's figure the arrow here is from C to E. Okay, and then the system is negative HS. Why negative? It's actually, in this case, is actually negative positive, negative positive, so we can have a negative positive over here. Okay, let's try another one. We have a previous block diagram that we have learned to reduce the block diagram to a simplified version. So in this case, we have many signals. Okay? We have many signals here. We have RS, we have V1, V2, V3, V4, V5, V6, V7, V8, and finally we have the output CS. Okay, just draw the nodes for the signal first, and then we can connect all the nodes with a subsystem, with the system. Okay, so we have over here is a connection between RS and V1. So RS in V1 is connected. There is no system there. There is no square box. So we can say that R is connected to V1. We have a unity system. We have 1. Okay. And then V1 is connected to V2 via system G1. Okay, to the right. And then you can proceed with next V2 to V3. So V2 to V3 is connection between the nodes, then there's nothing there on the assignment junction. So we can proceed with the connection of V2 to V3. We put it as 1. Okay, next one is V3 to V4. So V3 to V4 is connected. We have a system there, G2. And then from V3 to V4 as well, we have another connection. So here, okay, so it is actually here. Okay, there's nothing there, so we can put it as 1. Okay, and then V4 is connected to V5. Again, V4 to V5, there's no square box on the assignment junction over there, so we can connect these two nodes with 1. Okay, and then we have V3 and V4 connection as well, but this time around we have a feedback. We have a feedback over here. So the feedback is actually H2. H2 is actually H2 and negative 1. So we have H2 and we have negative 1. Okay. Next one, we have connection between V5 and C. V5 and C. So the connection is actually G3 and a feedback of H3 and negative 1. Alright. And finally, we have another connection between V1 and V4 and V6. Okay, V1, V4, and V6. When we have in this connection here, we have negative H1. We have H1 and negative 1. Okay, that's it. And then we can simplify the signal flow graph here in figure B to figure C. Okay, we can simplify the signal flow graph here. So we can simplify between V1, V2, and V3 over here. So just multiply G1 and 1, we get G1. And then we can multiply again H1 and negative 1 between this connection. So what we get is only negative H1. Okay. So if you have done a few examples, you might want to skip step B over here. You just straightforward from the figure A to figure C, provided that you have enough sufficient exercise to find where you can simplify the nodes. Okay, so let's conclude that to draw the signal flow graph, we have to identify nodes, and then we connect the nodes with the system to provide us with a draft of the signal flow graph, and then we can finally, in step C, we can simplify the signal flow graph by eliminating the signals system with 1. Okay, when we do the signal flow graph, we can actually find the simplified version of the system. Previously, when we do the block reduction, block diagram reduction, we can find the simplified version of the block diagram. But again, with the signal flow graph, we can use the Mason-Gain formula. So the Mason-Gain formula can be used to simplify the block diagram. Okay, simplify the block diagram by using this equation over here. Okay, we have GS, which is a transfer function, which is the represent the ratio of CS over RS, output over input, and then we have a summation of TK delta K over delta. So what is K? K is actually the number of path. TK is the kth forward path gain, and then we have delta. Delta is 1 minus summation of loop gains plus, okay, this is a minus, plus, minus, plus, minus. So alternate. Okay, so we have 1 minus summation of loop gains. We have a plus summation of non-touching loop gains 2 at a time, minus summation of non-touching loop gains 3 at a time, and so on and so forth. And delta K is delta minus summation of loop gains terms in delta. This is delta actually. Okay, this is delta that touch the kth forward path. In other words, delta K is formed by eliminating from delta those loops gains that touch the kth forward path. So just leave it as the definition here. So I will show you the examples that will give you more detail of how to do the block diagram reduction using SFG and Mason-Gain formula. Okay, so this example 1 here. Find the transfer function CS over RS for the signal flow graph in figure shown in the lecture notes here. So we have here, okay, first we identify the forward path gain. So what is the forward path gain? Forward path gain is we want to find CS over RS. So the forward path gain is the path that connect R to C. The forward path, meaning the arrow is to the right, meaning is the arrow from R to C. So we can find the arrow here is represented by this. Okay, this path. This is the only forward path that available in these examples. Okay, so we have G1, G2, G3, G4 and G5. Okay, that's why our forward path is here, G1, G2, G3, G4 and G5. The second one is we identify the loop gains. Okay, we identify the loop gains. Okay, the loop gain is form of loop between the nodes. So the first loop here is we have between V4 and V3. Okay, we have G2 H1, and then we have G4 H2. Next we have G7 H4. What else? We have another big loop over here. We have G2, G3, G4, G5, and then we have G6, G7, and we have G8. Any other loop? I think we only have 4 loops over here. Yes, we have 1, 2, 3, 4. This is the 4 loops, loop gains. Next, we identify the non-touching loop. Okay, we identify that non-touching loops taken 2 at a time, meaning that we have loop here where the loop does not touch each other. The loop that does not touch each other. Okay, so we have here is let's just erase first. We have 4 loops. Now we have the first pair. Okay, the first pair is G2 H1, G4 H2. This is the first pair. And then we have G2 H1, G7 H4. And then we have another one, G4 H2, G7 H4. Okay, what else? How many pairs we have? 1, 2, 3 pair. Okay, so we have 1, 2, 3 pair. Okay, so finally we must find the non-touching loops taken 3 at a time. So in this example, we only have 1 pair of loops that does not touch each other at a time. So in this case, we have G2 H1, G4 H2, G7 H4. This is 3 non-touching loop at a time. So all these 3 loops does not touch each other at a time. Okay, so we only have 1 pair over here. So loop 1, loop 2 and loop 3. Okay, so now we have find all the loops. Okay, we can use the Mason gain formula and we can find the delta. So the delta, remember, is 1 minus loop gains. Okay, loop gains, how many loop gains we have? We have 4 loop gains. 1, 2, 3, 4 loop gains over here. So 1 minus 1, 2, 3, 4. Okay? Plus, so minus, plus what? Plus 2 non-touching loop at a time. So 2 non-touching loop at a time, we have 3 pair. 1, 2, 3. So we put it in this equation. 1, 2, 3. And finally, minus. Minus what? Minus 3 non-touching loop at a time. Okay, so we only have 1 pair. Not 1 pair, we only have 1 non-touching loop taken 3 at a time over here. So we put it into the formula. Okay, so the sign, you must see the sign over here. Okay, the sign is minus, plus, minus. So it's alternate. Okay, and then we have a delta 1, since we only have 1 path, meaning that we only have delta 1. So this formula is actually, we can have 1 minus loop that does not touch the forward path. Okay, this is loop that does not touch the forward path. Okay, so in this case, we only have, so this is our forward path. So from this figure, we only can see only 1 loop that does not touch the forward path, which is G7 and H4, G7, H4. So we can put it into the formula here, 1 minus G7, H4. Okay, so now we can put all together into the Mason gain formula. We have T1 delta 1 over delta. So T1 is the forward path. The delta 1 is actually this one. So this is the delta 1. Okay, and then delta is actually this one. So in these examples, that's not shown in this formula because it's quite long. Okay, that's it. We already find the transfer function for this example. So we have another example here, example 2. So for the example 2, use Mason gain formula to obtain the transfer function of the system represented by the following signal flow diagram. So the first is method, or the first thing that we need to do is to find the forward path. So when we say the transfer function is, we want to find the G. Okay, we want to find G, which is CS over RS. So we find the forward path between RS and CS, which in this case we have 1 path, and then we have another path is actually here and here and here. Okay, we must take into consideration only the forward path, meaning the arrow is to the right only. Okay, so we have T1 and T2 this time around. Okay, so our T1 is G1, G2, G3, and our T2 is G1, G3. Okay, 1 G1, 1 G3. So we only have G1, G3. For T1 we have 1 G1, G2, 1 G3. So we have G1, G2 and G3. Okay, now let's find the loops gains. Okay, the loop gain, we have G2 negative H2, we have G3 negative H3, and then we have another one, G1 G2 negative H1. So we have loop gains, 3 loop gains. Okay, 1, 2, 3 loop gains. Now let's find if there are loop non-touching loops taken 2 at a time. So we have only one pair. We have actually 2 pair. Okay, we have G2 negative H2, and we have G3 negative H3, and you have another one which is G1 G2 negative H1 and G3 negative H3. So we have 2 pairs. Okay, we have 1 pair and we have 2 pair. Okay, now let's see if we have 3 non-touching loops taken 3 at a time. So we only have no non-touching loop taken 3 at a time. We only have only have up until 2 non-touching loops taken at a time. Okay, so we already have all the information necessary for to do the Mason's gain formula. We now have our delta, which is the delta is 1 plus loop gains. Okay, loop gains. So we have 3 loop gains, G1, G2, H1, G2, H2, and G3, H3. So actually we have negative, negative, negative here. So but we have 1 minus loop gains. Okay, that's why minus multiply by minus, we have positive, positive, and positive over here. Okay, next we have 1 minus 1 plus loop gain, non-touching. We have we have non-touching, 2 at a time. Okay, non-touching 2 at a time. We have 2, which is plus G1, G2, G3, H1, H3, and then we have G2, G3, H2, H3. Okay, we have delta 1 and delta 2. So delta 1, okay, delta 1 is so delta 1 is actually, so again our forward path is here. Okay, this is forward path. So if can you find out where we have a loop that does not touch the forward path? No, right? So the formula is 1 minus the loop that does not touch the forward path, which is nothing here. So we have delta 1 equals to 1. Similarly, we can find the for T2. So can you find the loops that does not touch the forward path T2? So everything is connected to, even this loop is connected to loop the forward path T2. So there is nothing as well. So we can say that our delta 2 is equals to 1 as well. And then when finally we can put together into the Mason's gain formula, we have here basically we have a summation of Tk delta k, where we have delta 1, T1 delta 1 plus T2 delta 2 over delta. So we put together all the information that we have found previously into this Mason again formula, and we can find the transfer function of the system. Okay, so now we have come to an end of this signal flow graph topics. So I hope you can understand, and please go back and do revisions, because we will use this a lot in the next coming chapter. Until then, see you and goodbye.